Hello, hello. Hi, everybody. Just like to be the first to welcome you to the 2025-26 Colloquium Series. Yes. I want to first, So this is the schedule that we have so far. Today is Research Improv. Coming up, our next speaker is one of our very own, Sue Becker. We wanted to feature some recently retired profs just to kind of continue the knowledge and so people who are new here might know a bit of the department's past. Ian Bruce, Ed Hagen, Mark Schmuckler, Brad McIntosh. We're always looking for suggestions, so if there's someone you'd really like to hear speaking, please get in touch. And I guess another kind of philosophy this year is to really involve grad students, and we're very pleased to have a big team this year. So as I understand it, 2 years ago maybe, or 3 years ago, there were 2 grad students working with David Shore. And that was sort of the post-COVID reemergence of the colloquium. And with each year, it's grown. So we're really building off of what Luke and Zoe and David started up. And now we've got Luke and Shane, who are kind of our senior advisors of the grad students, but we have a whole new group of grad students, Alex, Emma, Jonathan, Karen, and Tong Tong. Okay, so it's really great. It's really great to work together with students. And so we really want students to feel like they've got, a role in picking our speakers as well. So look out for questionnaires that we send out. I know some people answered those. It was very helpful. So today we're doing something, I don't know if 2 years ago was the first time ever that David proposed this research improv. And it was so much fun. I was a brand new faculty member here at the time and just got to, kind of make fun of my colleagues, I guess, is the name of the game. So let's get moving. So we're going to have Luke as our MC today. I think we have 5 or 6 different research groups. 7. Oh, wonderful. Great turnout. So Luke will explain the general gist, and then we'll get started. All right. But anyway, welcome. And one other thing, we're having a reception afterwards like we always do, but we're going to try it out doing it in the lobby this year instead of going upstairs. The idea there was really just we want to maximize the number of people that stick around to take part in the reception. So let's all stick around today and make that a success so that we can feel happy about our decision. All right, thanks.
All right. I think I can go to the next one here without revealing anything. All right. First of all, I want to thank John and also Katrina, the 2 new faculty members in the position of organizing colloquium, and it's been really awesome to work with both of them. So I'm going to be leaving my role as part of the colloquium committee, but I'm really excited to kind of hand it off to these new folks. So, all right. So I like to have fun. I value fun very highly. And that's what this is about. So, and it's also about thinking on your feet. So what we're going to do here, if it hasn't been explained already, is we have 7 sets of slides that are coming up. And we have 7 volunteers who have made those slides. Thank you so much for all the grad students who have volunteered. I'm excited to see what you'll do. The people who will come up have not seen their slides yet. And they will attempt to improvise a presentation as best they can. And then at the end, we'll give you a little QR code and you can go on and vote for your favorite presentation. And so the point is to make it entertaining, to make it fun, and also to learn a little bit about what the labs are doing. So labs as a whole have made these presentations. So it might be just one person's research, or it might be kind of a smattering of research by different people in the lab. Regardless, after each presentation, the person whose slides were just presented will have a chance to come up and correct anything that was horrendously wrong, and hopefully make a few jokes. And we're all here to have fun, and I think don't be afraid to poke a little fun at your colleagues. Okay, so thanks for indulging in this process. We haven't really done this before, except for a couple years ago, and now we're trying it again, and let's see how it goes. Okay, so without further ado, let me bring up our first contestant. Give them a round of applause.
Why'd you make me first? Oh gosh.
Okay, you're gonna have 5 minutes.
Okay.
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 To do with what you will.
Okay.
Are you ready?
No.
Perfect. Here we go. Welcome, Alex.
Oh my goodness. This is perhaps the most groundbreaking study we've seen in a millennium. This should be on the cover of the next Nature article. As you can see, there's quite a few infants and they're developing, so maybe it's development. We can see that we are measuring cortical area by some abstract units. I'm going to say millimeter cubed, and then we are, millimeter squared. And then we're also measuring their age in years. So this is a very, very long longitudinal study. And what we see, is it a longitudinal study? What we see is that quite obviously in the left hemisphere, as you can see, in one of my favorite brain areas, the left premotor and motor cortex shows quite a bit of activation. No, not activation, proliferation, and activation. and we see that as you grow up, you show more deactivation throughout these same areas, actually the whole brain. So what this study is telling you is that actually the smartest people are those that are aged 4 to 10, and after about 20 years old, you don't see any activation, you just see deactivation. How am I doing on time?
Reminder, there are 3 more slides.
Oh my God. But yeah, rhythm perception. And then if we go on to here, we see that the motor area here is actually interacting with this anterior temporal gyrus, I guess. And they're communicating with each other, but there's this feedback loop, and when we feed into the motor cortex, we know what's going on. But then when you're older, like you're 20, you move, and then you get this like feedback loop into your anterior temporal gyrus, and you just don't know what's going on. And that's that deactivation. We're just dumb when we're 20. That was what we're saying. And then we see that if we were to put a cap, I don't know what kind of cap, let's say it's an F-Nears cap on, or whatever cap on the human while we're 20, we see a lot of activation in these motor areas, so we're still functioning, we're just moving around, but we get deactivation in all other areas because we just don't care. Is that my last slide? No, okay, oh my. So this is actually, scratch everything I've said, this is about coupling, and this is about drum circles, and what we're seeing is that we get, as we develop in age, I'm guessing it's a drum circle, just based on who submitted slides, but we see that when we have activations, or we have linkages between participants in like a quadra, I don't know the word, four, in a group of four, we get a much more, why is it more disruptive when it's just one link? That makes no sense. Scratch that. This experiment didn't work. We're actually we're pulling the manuscript from nature, and what we see is the opposite of what we'd expect, where there's strong coupling when there's a lot of interactions between the groups of four versus just one input-output source. I don't know why, but isn't that science, guys? Oh, there's one more? And then this is actually, scratch that, this is our actual new best project, and this is what's gonna bring in like millions of dollars of funds into the PMB's department, is our juggling study. So what we do is we take non-jugglers and we put this saw-like contraption on them, and then we force them to learn how to juggle. And as we can see, when the Earth and the Moon interacts, it creates this spatial like locking in phase where you're able to map your hand movements, and you're juggling on the moon, but you're better on the moon because there's less gravity and you have more reaction time. I don't know. But yeah, we find that jugglers are better jugglers on the moon than on Earth. Thank you.
Thank you. Okay, I loved that. I loved every second of that. All right, whose slides are these? Whoever's they are, please come hither. No, we know. We know whose they are. Okay, so now what we're going to do is we're going to take 3 to 4 minutes, or however long you need, but don't take too long, to please give us a short explanation of what is going on in these slides.
Okay, so yeah, I'm going to try and keep this quick. This is 4 different studies. This is not all one cohesive set of data. Here, what we have is the role of music in development, and the major highlight from this is that over time, we're seeing in people with music training more, I think, increases in cortical volume in motor and premotor areas, and that there is a positive correlation between rhythm perception ability and your motor and premotor volume. That's going to be my really concise way of explaining that. This is exploring John's, I'm from the Everson lab. My name is Jonathan Kirsch. If you don't know me, just introduce myself, because otherwise I feel like this doesn't make any sense. So this is evidence in support of the ASAP hypothesis, which essentially predicts that motor regions of the brain are recruited when you're perceiving rhythm, and that they're actually providing a structure to the audio that you're hearing. And this is supported by an EEG study where there is bidirectional flow of activity between auditory and motor regions. So that's super cool. And then this is indeed a drum circle. So my study is looking at drum circles, people participating in a drum circle under various conditions that don't exist in the real world. The first two do exist, so this is just a pair of people who can hear each other, and that's great. And you can see some pretty cool stuff here, some leader-follower dynamics here where, you know, this person speeds up a lot, and then the next person follows them, and then they slow down, and the same thing. The other person follows them. And then the reason that these are different is in this group of four, everyone can hear each other, everyone can hear everyone else. In this group, you can only hear the person to your left. And that creates a lot of really weird synchronization strategies. People are trying to like assert dominance over the drum circle. And it's kind of like a game of broken telephone where it goes around and around and around. And then finally, we have people juggling on the moon in VR, which is really fun. Juggling is, if you've ever tried it, really difficult unless you're in David Shore's lab, in which case you're really good at it. But you know, why don't you try juggling on the moon? It's, you know, reduced gravity. It might be a lot easier. So we have this, this setup called the spider, where you have these balls attached to strings that increase or decrease in tension based on whether there's something in your hand in VR or the level of gravity. And then we have various visual conditions. So for example, in the vignette on the top right there, we're trying to see that if we cut off an area of someone's vision, are they still able to juggle as well as they would otherwise? And yeah, we still have some, we're still collecting data on this, but just some preliminary stuff. We show that this y-axis here is just the number of bouts, so just how many times can you keep the ball up. It does increase over time and is still pretty strong in the vignette condition when your vision is blocked, and that's about it.
Are you ready?
I'm ready. Ready?
All right. Here we go.
All right.
Please welcome Jonathan.
All right.
There's animation.
There's animations? I think I'm going to need them. The mind. What a concept. Stick with me through this. Oh yeah, okay. I know exactly what this is. Over here, oh wait, no, sorry. Okay, this is solid. So what we're looking at here is increases in cortical volume over time, but you wouldn't know that just by looking at it. With these cool waves, actually the areas in black are areas where you know, this is ridiculous. But as you can see, we found a significant difference between the two. And that's what's the most important part. But enough about that. Now I know what you're thinking. You got a running response and a freeze response, and we're looking at differences in those responses between male and female rats, probably. And you can see, what can we see here? Well, in male rats, we're seeing more of a running response than in female rats. And then in female rats, we're seeing a freezing response only sometimes in non-match trials. And now you're asking me, Jonathan, what's a match trial versus a non-match trial? And I gotta tell you, if you don't know, you gotta call me after this. Now right here, enough about that. I know we've heard a lot about that today. Here what we're looking at are two curves, and they're actually spectrograms of audio that we've presented to rats when we're having them conduct a run or freeze response. And you can see that in the run response condition, we see a significantly higher levels of, let's say, serotonin. That's what I'm going to go with. This one is rough, gang. I don't know what we're going to do. And enough about that, because we've looked at that a lot. Whose slides were those? That was it. Well, that was all right. We made it through that one. Whose slides were those? And meet me outside after this.
Oh, it was you? Yes. Okay, Jack's coming down.
told me before that his were really rough.
The point of this is to just get a nice big overview of everyone's stuff, so I think we're accomplishing that. Great job, Jonathan.
Okay, thank you.
So there was a bit of a last minute change. Those were not slides that I made, but Aisha and my lab put them together. So Jonathan actually did exactly what I would do, so he kind of nailed it. I can give you a gist of what this is, kind of, but not actually, because I don't know. So no, there's a conflicting meeting. So, graphs like this in my lab normally, we get them when we put an implant in a mouse's brain. This is likely a reading of signal from the mouse's PVN, the paraventricular nucleus of the hypothalamus, which is the social hub in the brain. And one of these lines was likely from a mouse that was deficient in catnap2. It was a knockout of catnap2. Catnap2 is a gene that is related to autism-like symptoms in mice. So what likely is happening here is this one, there was a mouse and there was a thing in its head and it was recording activity in the PVN, and whenever the mouse socialized with another mouse, we marked that and then standardized it to like the middle. So whenever, like this is like a timeline of like the mouse is what it's doing, and then this is the point when it interacted, and then we took those action potential signals and put them together, and they're very different, like Jonathan mentioned. So this is, if you have questions, I think this is Ash's work, if anyone. Yeah. This is, I can do a bit about, this is more to work off of. This is a looming shadow task. So the mouse is in a box. It also has a thing connected to its head, and then a black circle appears. So you can see that right there above it, and then it gets bigger and then bigger as if a predator were coming up. And then these graphs record what's going on in that same spot, probably. Or it could also be recording oxytocin levels, potentially. And then those are running and freezing responses, what they do when the black circle comes. And if you have questions about that, talk to Katie in my lab, or Anita. Anita's a good person too. I think, so these are spikes for sure. Probably, I think there's just single cell recordings from neurons in the D1 section of the, yeah, you're gonna have to talk to Aisha about this.
I don't need you to improvise too, but I'm about to do one. So. Okay. I'll remind you that everyone made these as a lab, so this might happen again. Where it's not just the one person's work; it's a lot of people. So, are you ready?
Sure.
Okay. Let's go. And your moment in the limelight. Here we go.
All right, hi everyone. Welcome to my work on moving dots. So typically when you're out at like a disco or something, or in the club, there's all these different dots and they move in certain ways, and we wanted to see what happens if you put a whole ton of people in the dark and put dots on the screen and move the dots. And what we saw is that when you make noises with the dots, like when the dots have like a little noise that goes along with each colored dot, it helps the audience move with the dots. The audiences blink. They move, they blink as the dots blink and move, depending on the color of the dot and the sound that it makes. Now with that, we also, before our study at the club with the moving dots, we actually taught our subjects a dance, and it kind of looked like this. It was step, clap, and then they held the dots. So each person was also holding these colorful moving dots that made noises in this second part of the study. So the dots on the screen were actually people, other people. It was a recording of other people holding these moving dots. Yeah, and this is just kind of describes that. And then the speed at which we made people dance with the dots, that changed how fast they clapped. And then we took our dots, we said, you know, this is a pretty cool study. What if we put these dots onto babies? And what if we go beyond dots that are filled in, and we just took markers and we drew on people's faces? We really wanted to push the boundaries as to what a dot is and isn't. And then as you can see, when the dots were on someone's eyes, they were more likely to sing. And then when the dots were on someone's mouth, they were more likely to talk. Right. So, we really wanted to hone in on the noises that the dots were making and how that was changing behavior. So we put same people in the room with the moving dots. We gave them headphones, and then we changed the noises that the dots were making in people's hands. And the noise, because everyone was wearing headphones, no one could hear what was going on in the room. And so just typically, okay, you probably don't know this because you've never put on headphones when you're looking at moving dots, but typically, when there's moving dots and no one can hear everything, people will imitate the noises that they hear of the dots making. Yeah, so that's what this graph is. It's the noises that people were making when they couldn't hear anything in the room. Yeah, that's what it is.
I want to hear a chorus of dots now. I just do.
You are so fixated on the dot, Jack. So I'm Shu from the Trainer Lab, and well, this is a live lab study, and VLF is the keyword here, and it is very low frequency. If you look at panel C, it is below 40 hertz, so we can't hear it, nor we can perceive it, according to panel F. But people move a lot more when these very low frequencies are on, when you look at panel E, which means that if you go to a live concert and there's like a lot of booming noise, even if you can't hear it, even if you can't detect it, you're gonna dance a lot. And the dots were actually each single person in the live lab, like in the panel B, and the color is essentially the speed of the movement. So I don't know which condition it was, but it's a moving dot is a dancing person. And that's it about dots. This is, and that was Dan Cameron's study in our lab. This is Chantel's study. DCD is the keyword here. It is a coordination disorder. And Chantel had kids do a step, clap, dance. and see how well they do. And essentially, when the metronome is a lot faster at 400 milliseconds, the DCD kids perform worse at the task. Panel A on the top right essentially shows how we calculate the synchronization of head marker movement to the rhythmic auditory wave. So that's that. And then this is Sarah's study, Sarah Ripley's study. This is a different study as well. It's a mother-infant study, and it examines how the caregiver and infant looks at each other during infant-directed song and infant-directed speech. And she essentially analyzed the eye movement and had an analysis on where the eyes were fixated on, either the eye area or the mouth area. And the biggest takeaway, I think, is caregiver and infants look at different areas of the face. Is that it? Okay, cool. I know that. And this is my study. The left figure is the analysis schematic. The right figure is the result. Essentially, you listen to one sound or two sound, panel A, panel B. We extract the temporal or the spectral feature of the sound. Panel C, we model the two sounds as either separated sounds or combined sounds. Panel D, we do a reconstruction / decoding. And on the right, you can see that the separated model wins at a very early lag. This is easy, by the way. And you can so see that when looking at spectral tracking, the brain separates the two sounds at a very early stage of processing, 50 to 100 milliseconds. And I guess that was a little too hard, Jack, sorry. Okay, so, okay. Oh, well.
Whenever you're ready, press the button.
I'm Shu from whose lab? I don't know. Oh, this is, I know whose it is. Oh, this is spatial attention, right? And we want to look at how we direct attention on differently salient stimuli. And obviously the blue triangle, no, home base is very salient. So we try to measure the reaction time by varying the direction of the home base and the color of the home base. I guess that's close enough. Oh, okay, so it's a continuation. Nice, Ben. There is a fixation for 1,000 milliseconds, and then there's a blank screen for 500 milliseconds. And then you're going to be presented with a single item, which is going to be your target. That's going to be either the color or the orientation of the shape. And after a random 500 or 1,000 millisecond blank, you're going to be presented with a singleton search task, where you would hit the screen. There was a predetermined condition, actually, that the participants were taught to think of blue, and blue was sort of the target color, regardless of the single item. Screw what I said in the slide earlier. And yeah, there you go. If you look at the reaction time of blue and orange colors, you can see that when you're told go blue, you react a lot faster to blue colors, and that when that is the search target color. And when you're told go orange, you react a lot faster to the orange stimuli. And interestingly, when the single item color is orange in the go orange condition in the blue task, you also react to orange colors faster. I guess that's it. How did I do?
Thanks, Shu. That was very good.
Okay.
I wouldn't have expected anyone to get much closer. So, I mean, my slide. So I'm Dr. Ben Sklodnik, and I'm here representing the Millikan lab. And this is, of course, my research. And what we're interested in is, in general, a basic feature of attention is that you're drawn to things that are physically distinct in the visual field. I'm being mocked already. So, for example, it's hard not to look at this blue home base, which is a diamond that's missing one of its corners. And so one of the classic questions, an age-old question that is yet to be fully answered is, do we have control over this sort of automatic capture by distinctly salient things? So my PhD work was really based around coming up with a method to induce preparation, get people prepared for a particular color to see if we can measure top-down control in a pop-out search task, and also to look at effects of priming. Priming is another thing that can affect our visual attention. So we want to get all these things in one method and then see if we can measure influences of top-down control and priming in a context where you also have a strong salient target pulling your attention to it. And so we have this method where you get a single item and then a search display, and you skip this animation. There was one animation that's my bad. I didn't know what the rules were, but we tell people in some conditions, for this first thing, respond only if it's blue. It could be blue or orange. And the reason we do that is because then throughout the whole task, people are getting ready for a blue thing. Then you get a search task at the end after each single item, and then you just respond to the odd color. Could be blue, could be orange. So you have this go for blue for this first task, and then for the second task, you just always go to the odd color. And we're really clear. It's like 2 separate tasks, but we just have this first task just to trick people into getting prepared for blue or a particular color. And so we might expect that when people are prepared for blue, they might be faster when the target's blue than when the target's orange, if something like top-down preparatory control can influence attention in a pop-out search task. And so just as Shu said, when you're getting ready for a blue thing, you're fast when the search target's blue and slow when the search target's orange. And it actually doesn't matter what color the single item is. It doesn't matter if you responded to it because it was blue or ignored it because it was orange. It's all about this top-down preparation state, which is cool because some people, especially older researchers, there's a long period of time where people said, no, if you have a salient thing in the display, that's what will drive attention. And something like preparation, it shouldn't really influence search. But here we show really strong effects that it does. And we're still working to understand why. Just go, yeah. These are like tough acts to follow. Yeah, so I've been here a long time, and I've always imagined giving the colloquium talk, and so I'm really excited to talk to you about my research on performance. I definitely have. I work with Bruce, but you'll find me in the live lab every opportunity that I get, and so here I'm just starting with a smattering of all the different events that I've run, studies that I've run. In the top left, truth is a knife. If you know, you know. This guy, Ellison, I forget his name. He plays a really small guitar. That was really interesting. And of course, we have dancing studies of vision and people talking about vision, the mimes. And so I'm going to talk about, in general, the overarch. This is, of course, just my research that I do on the side when Bruce is, busy with other things. And so the overarching thing that I'm interested in is how we can probably make performances more enjoyable for audiences. And so the first thing that we did was we thought, well, let's give everyone a watch. And glasses, because it's important that when you're at an event with people, there's something really important about group cohesion. Like when you're there as an audience member, just like you folks now, you're all experiencing the same thing together, and that's important for how you end up, I was going to say the experience of the experience. Your experience of this event depends on the cohesion together. So, of course, the first thing we want to do is give everybody the same glasses and same watch to increase that cohesion, and we make them put their phones away. And these are the diagrams of how the glasses and the watches work that we just have to show you because it's patented information. So we just promise the companies that we put those schematics up so that it can't be copyrighted. Okay, and of course, if you've heard Bruce talk, the world's changing rapidly. That's something we care about in our lab. We care about thinking about how cognition and the things that we know can be used to inform all of us, the general public, about how to navigate the crazy world that we're living in as information processing changes. Like in the first studies and the smattering of examples I showed you, we're thinking about an audience in the context of a theater like this, but in this case, in this sort of broader step that I'm taking, I'm thinking about society as an audience to the main stage that is news media and politics. And so it's just sort of an abstraction of this idea, thinking about group cohesion in the context of a performance. And you can see this is for sure a performance. And so what we didn't tell people is that the glasses that we gave them can actually identify who they're looking at and send that data to us. Okay, just a final thing. This is, you might not know it from ooh, I might get this wrong. I'll just run with it. This is no, yeah. Okay, so in all of the studies I just talked about, we give people an experience and then we take them aside afterwards and we want to measure the effect of the experience on their social cognition and the group cohesion. So we like have an event like this, for example, but in the live lab, of course. And then after the event, I'd say, okay, get into groups of 4 and then do a task together, right? And depending on, so like, for example, this might be a group of 4 people. These people may have got the watches and glasses, so they all look cool together. Another group of people may have not got those things, and they would have just been left to whatever they were wearing, and they might feel like outcasts. And then what we can do is put them in some sort of simulation game that simulates their tendency to lie or cheat or cooperate. And what you can see here is that depending on how many windows are in the room, actually, it's completely surprisingly, it was an extraneous factor, but it turns out that, yeah, actually, no, yeah, sorry, I've misread the plot. The main difference is between the colors. So you can see the darker bluish colors are the people who had the watches and glasses, and they show a higher effect of more likely to share and be social. The yellower, warmer colors, those are people who were left, didn't get included in that fashion manipulation. And then what we wanted to control for, because the live lab has all the windows from the whole building. So there's like the building, and then when the live lab was built, they took all the windows and put them in the live lab. So it was really important because I don't have windows in my office, and that's for experimental. That's so that I work the same depending on what time of day it is. It's about control. So it's really important whenever you run anything in the live lab to make sure you control for the number of windows. And we can see that, importantly, it doesn't matter. It was rough.
I mean, you nailed it. You nailed
Well,
it. Really, I couldn't have said it better myself.
We have, I think, 3 more.
Okay, I'll try to be quick. It can be quick. Oh, I have to go backwards, obviously. Yeah, so we're interested in large group social situations like this. We want to know what's going on when people have these meaningful social experiences. It could be things like music or dance or theater or mime or a pop-up art gallery or even a watch party of a political debate, right? But the thing is, we don't really have the tools to study people in these kinds of contexts. So that's what Live Lab was built for, and that's some of the methods that my lab has been developing, why we're developing them, right? We just need better tools to be able to kind of get at some of the lower level mechanistic, cognitive, neuroscientific underpinnings of what's going on in these interactive social situations. So that's what I've been doing, is developing tools. It is, in fact, patented software for multi-person mobile eye tracking, but it's our patent, it's Shresh's patent. So that's Shresh and my work. And then the watches are Maya Flannery's work sitting right here. The tablets and the link to online is we've also been doing a lot of web development so that people can join our live streams. I think we have an online audience, watching Colloquium today. So to hopefully be reaching those people also more like as we move towards more hybrid social situations, we want to be able to measure those things. So these are like the tools we've been developing to do that. Love the idea that it was a fashion manipulation though. And I was recently at a visual aesthetics conference, and this fashion guy started his talk by saying that people spend more disposable income on fashion than music and books and all kinds of other things combined. So maybe we should be studying fashion. This was supposed to play. Did you guys take away my video? That's why I shared a link. That's why I shared, okay, because this was going to be an example of like NDP and conservatives arguing, and you were going to see, it's a heat map of where our whole Watch Party Live Lab audience is looking as the politicians are arguing. And I was going to say, okay, well, we also want to understand what's going on when people cooperate or don't cooperate, and whether we can also build tools to make people more cooperative, and that's what this slide is kind of about. Yeah. So if you could see the animation, it was like an argument, and he was about to say to Steve Piken, like, I want to talk now because like NDP just made me look bad. So it was probably motion-based. He was starting to raise his hand, and then, yeah, so it's a bad frame to pause on. Yeah, it was motion. Okay, so cooperation, or lack thereof, because those politicians were not cooperating. Here we built a little assistive device to try to make people cooperate better. And what we're doing, if you know a metronome from music world, it's just a device that helps you keep time. And we actually can change that metronome in real time. I had kind of schematized that with the little center setting icon. And I thought that we were supposed to remove all text, so I'm sorry that window was still there, but it was a great joke. So anyway, it's the time window of the metronome on the x-axis, and then how much it's like the asynchrony of all these people tapping together on the y-axis. And if they're tighter together, that means they're more in sync, and we can show that that synchrony makes them more cooperative. But the cool thing about this system is we can push it around, so making people more or less cooperative based on how adaptive our little system is. So that's what that was. Okay, now I need to talk about someone else's slides. All right. Well, color is a super important part of our visual world, and there's lots of colors, so we can choose one. So this is commonly called a color wheel. We could talk about hue and saturations and all kinds of things there, but I think the thing is, if you were already looking at red, then you saw gray, then you saw a color wheel, then you saw gray again, no one's really answered the question of what happens next. So we have to, and now we know. So that's what this is. That's what's going on here. So we can, well, it looks like we can reconstruct those color wheels. Some people, it's looking like people are pretty good at the colors on the edges, but some people aren't really understanding like a circle versus a kind of triangle. Things are getting warped. We're still, to my eye, we're still kind of getting similar color patterns. I think it's really just something about, when you see that gray, it kind of distorts your sense of a circle, and then you can't recreate all of it properly. Oh my goodness! And if you, yeah, and this really, I think if you show them more circles, you do get closer to that circular shape. And again, we're still able to see all the colors, so that's really good to know. We're still not quite sure if my red is your red, and you can kind of see that like this person's green isn't necessarily that person's green. So that's going to be an open question still for future research. And that's why we started moving to squares, actually. So that's what you're seeing here. And over here we had a kind of continuous color space, and over here we wanted to discretize that, block that, and between the left and the right sides, you can kind of tell that these are wider rectangles. Things are getting a little smaller over here, and we had two different groups trying to recreate those. And well, your guess is really as good as mine. How well they did. It's sort of like I was saying. It's hard to have a ground truth when we're talking about colors. And I'm actually not the first person to say that. Jerry Seinfeld said that first. The things that are coming to my mind, I feel like maybe they shouldn't be said. I don't really know. You could be a gold person. You could. I don't know. I don't really know. Some big stars might see color differently than we do. I think being a star distorts your sense of color. Hi, Aiden.
Hello, bonjour. Do I have to oh yeah. You don't know me by now? I am Aiden Knights. I am in David Shore's multisensory perception lab. You may have noticed me fall up the stairs earlier for your benefit. Okay, so we set out to measure, excuse me, we set out to measure mental imagery. We started with a very basic kind of working memory color task. So what happens is we show you a color patch, one of 36 different colors corresponding to 10 degrees around a color wheel for a total of 360 degrees, right? And then there is a retention interval of either 3, 6, or 12 seconds. And then a color wheel pops up and you identify the color of the stimulus that you just saw. And so here, this is, so on the y-axis, these are days. On the x-axis, these are participants, right? So participant 1, we basically wanted to see if there was any learning affecting the veracity of people's judgments. So perfect performance, you'll see kind of on the left side, like it's getting pretty close. Who's got that laser pointer? Who was that? You're getting pretty close to perfect performance, and you can see that there are just varying degrees of deviations. It seems to be pretty stable across days, so it seems to be kind of a more baseline phenomenon than just practice. And interestingly enough, the person on the right side is aphantasic. They have no mental imagery, and you can see that their performance is stable and kind of a little worse than everyone else's. Left side? Okay. This is essentially just showing you the same thing. What's really interesting, though, is that there is error is consistently biased in the green and magenta areas for most participants. Like across participants, you see these consistencies in bias. But still, you see that everyone seems to interact still idiosyncratically with colors. So you have this main effective hue, but you have also this hue by participant interaction. I'm just going to go ahead and skip over this one because it's not worth explaining. This reflects the truth I think we all know. What that truth is often said to be open to interpretation. So maybe I don't need to lay it out. There's no main effect of Tom Hardy, there's no main effect of Samuel L. Jackson, but there is, if Jerry Seinfeld's thrown in there, you get this kind of mysterious three-way, mystical almost, interaction. Yeah, I'm surprised Lauren didn't pick up on that a little bit sooner, to be honest. Okay. I hope so. Okay. Oh, I thought the screen was, okay. So this study, what we really wanted to know is how people felt about their country when we took the abbreviation of the country and placed it against a black background, right? So CAN here, that stands for Canada. This is a place that some of you may be familiar with. Some of you may have spent a little bit of time here, a lot of time here, but either way, we are all in Canada right now, whether you like it or not. Okay, well this is very close actually to the findings of Guglielmer et al. And it finds essentially that the first letter of the country when placed against a black background, what people tend to, they don't really want to think about that letter. They don't really want to think about it. So instead, they picture some horrifying kind of facsimile of a shelf that seems to be perhaps falling through the floor in somewhat of a derelict-looking location. The letter A, a little bit more popular when not placed against a black background. But again, people, they want to stray away from these standard representations. So they begin to visualize a cat that inside of it has a shelf and is perhaps in a castle, right? Looking out, because you can see the castle window there. The cat is looking out of the castle, right? Just remember the cat is looking out of the castle. Some of you know. And then the letter N, when considered against a black background, what happens is that people tend to go into a kind of phantasmagoric, like almost psychotic type of state, and they start thinking about toasters with arms that also might have some refrigeratory capacity. Oh my God, is this, I don't know if this, okay, again, see what we're actually more interested in here is, well, when you think of the weird shelf, what comes next to your mind? What comes next to your mind is a bouquet of flowers. For the cat refrigerator, letter A, it's maybe a lamp that has a genie in it. And then for whatever the heck I said before, you get everyone's worst nightmare. Perfect. So this is really what ties it all together. And this is what the inverse ratio of the Korkenheimer-Poken figure is based off of, that we're all so familiar with, right? So, you know, if you think about these three kind of concepts in conjunction, you get the shoe mailbox with the weirdness. And then if you think about these two things in conjunction, you get the slipper. Cinderella slipper, to be specific. And then, I mean, we all know what that other thing is. Oh, perfect. Okay, so again, so now we've moved to provincial, NS, Nova Scotia. And what you see, again, if you think about the color orange, and then you think about Nova Scotia, and you think about the color blue, it's going to be in a different place on the graph for some reason than if you do it with purple and orange, and then with some underlines and some stars on it. So, yeah, I mean, what else do you need to know, right? Oh, and you can see up top there that participants actually had to pay a fee to do this. Okay, so you can see in the temporary succulent gyrus that what would happen was when people would picture these horrifying images, is that their brains would actually begin to be on fire, right? So this is actually not neuroimaging. This is just the quality. This is a real person's brain that was thinking about this, but the quality of the image has also been damaged by the fire, much like the brain itself. Okay? And so you can see this person got a little bit more lucky. Less fire in the brain is always good. See, in this person, this is how you know that they actually hail from a different solar system entirely, because they don't react to the elements the same way we do. So their brains, as a matter of fact, when sprayed with fire, froze. Kind of like I'm freezing right now. Okay, there we go.
Thank you.
No, that was perfect. That was exactly it. But basically what we were studying was an fMRI study where we had artists try to be as conventional as possible, as aesthetic as possible, or as novel as possible, or can. And these are just examples of what people drew in the scanner. The main thing is that what we found, when you try to increase the aesthetics of your drawing, you also increase novelty. But when you increase novelty, you do not increase aesthetics. So these are the conventionality, aesthetics, and novelty scores. And really interestingly, this is not your brain on fire, but this is your brain on drawing. So this is what your brain looks like while you're drawing each of those images. And we had another condition. Instead of drawing, it was imagining what you are going to draw before you actually draw it. And we thought perhaps the activations would look very similar to when you're actually drawing, but that was not the case at all. We saw really mild activations for when you're imagining what you're about to draw. And specifically, we see kind of more low-level areas than we expected. But the fun thing is that the deactivations actually look really similar to what your brain looks like while it's drawing. So instead of your brain being more active or similarly active when you're imagining it, we saw these really strong deactivations that look like drawing. Yeah. And should I say, we're from the Neuro Arts Lab, where we do fMRI and creativity and conversation.
Do we have one more? All right, that was awesome. Thank you guys. Thank you guys for bearing with us. I really enjoyed that. I really liked how we got a nice big view of everyone's actual research. This gives you a little survey where you can rate the presentations. And that does it. So.
Please join us for a little reception in the lobby out here. We're going to try that out, and we'd like to see what everybody thinks of today's presentation. Thanks so much.
Thank you.